Okay, number 7. This was actually the lowest scoring question on the exam, with the exception of number 11, so I wanted to go over this one in detail. So we've got a group G, and then we're talking about this capital Phi being the set of all isomorphisms from G to G. So G is some kind of group, so maybe G is, Z7 or D4 or whatever. And then think about all the ways that you can, permute the elements of G so that it stays the same, pretty much, right? So all the ways that you can take the things in G and shuffle them around so that you still respect the group operation. So if you think about all the functions from G to G, or even just all the bijections from G to G, there's a lot of them. Most of them are not isomorphisms. Most of them do not respect the operation, but some of them do. And so the set of all of those functions which do respect the operation and are bijections, that's what we're talking about. That's what we're talking about. So there might be a lot of them. And if you compose them, if you do one after the other, well, then you get a new function, and so that's the operation that they're talking about. So let's start by picking two elements in there. I guess I'll draw it like that with a capital. Actually, that looks stupid. I'll do it like that. So what does that mean? So that means, whoops. Oh, geez, what the heck? So that means F and G are both functions that map from G back to G, and they're both isomorphisms, right? So they're both bijective and homomorphisms. So then what about F composed with G, right? So why don't I actually write this a little bit differently? So F is an isomorphism that goes from G to G. And then G is also an isomorphism that goes from G to G. So if you just kind of like put those together, well then it's clear to see then, and this is also an isomorphism, so it's clear to see that F composed with G, or I guess that's the wrong way around, isn't it? Right, do F and then do G. Well, that would be an isomorphism from G to G. Now, why does it have to be an isomorphism? Well, because it respects the operation, right? If you have, if F respects the operation, so F of A times B is the same as F of A times F of B. I guess I should use a star. If that's the same as F of A times F of B, and then G does the same thing, well, then surely it's the case that if you do G on top of that, well, that's the same as G of this. And then G respects the operation too, so that's got to be the same as this, F of G of F of A times G of F of B. So the point is, because they both respect the operation, then so does their composition. And also, because they're both bijections, then so is their composition. So G composed with F is also an isomorphism from G to G. So phi is closed. Okay, what about the identity? Well, sure, let's use the letter I to mean the function which goes from G to G and does nothing, right? So it's the identity function. So in other words, you plug something in and you just get the thing. Well, then it should make sense that if you compose F with I, so some other function, F with I, or you compose it this way, those are both saying do nothing and then do F, or the other one's saying first do F and then do nothing. So of course, that's the same as doing F, right? So with respect to this operation, the identity function is the identity element of the group that we're talking about, of phi. So I is the identity element of phi. Okay, so we have the identity element is in there. And then finally, what about inverses? Well, if you've got an isomorphism F that goes from G to G like that, well, it's a bijection. So there definitely should be a function that goes back the other way. F inverse, right? Bijective functions have the inverses. But does it have to be an isomorphism? Yes, it does. In fact, it should kind of make sense, right? If it preserves the operation one way, then surely it's going to preserve the operation the other way, you know? But you can prove it like this. I just find the proof a little confusing personally. So we know that f of a times f of b is the same thing as f of a times b, right? Because f is an isomorphism. So then we can go from there to learn stuff about f inverse, right? If we apply f inverse to both sides, well then what does it say? It says it cancels on the left, so we just have a star b. And then on the right we have f inverse of this product. And then we can even write it like this. This kind of wacky looking way that I'm about to write it. Right, this is the same as yeah, this is the same as this. Right, so this sure looks ugly and complicated, which is why I don't like thinking about it this way. But ultimately what this is saying, oh geez, get back there. Ultimately what this is saying is that if you've got any two elements, f of a and f of b of G on the right, right, so this guy and this guy, this guy and this guy, that yeah, multiplying them, doing the inverse function to them first and then multiplying them is the same thing as multiplying them first and then doing the inverse function, right? So ultimately this is just showing that the inverse function respects the operation. So yeah, so there you go. So f inverse is an isomorphism of G. Okay, so the point is whenever you have any group, then the set of isomorphisms from that group back to itself is actually a group in its own right, right? So there's like an associated group of isomorphisms for every group that you start with. So that's kind of cool. The example that they want to go over is this one. Right now, what is Z3 exactly? Well, it's the set of, there's a couple ways to define it. I like to define it this way. It's a set 0, 1, 2 together with the operation of addition mod 3. So you can also define it like this as like the set of equivalence classes and stuff, but personally I think that's a pain in the ass, so I'm not going to do that. I'm just going to call it 0, 1, 2 with addition mod 3. Okay, so now let's figure out what's phi. Well, it's all of the automorphisms of that group. So you got to think of all the ways that you can map Z3 with some isomorphism back to itself. So I accidentally just used the word automorphism. That just means an isomorphism from a group to itself, which so that's exactly what we're talking about here. So if I've got an automorphism, what are all the ways that you can do that mapping? Well, big restriction. I know that an automorphism, or sorry, an isomorphism always maps the identity to the identity. So I know that 0 goes to 0. That is forced upon me by it being an isomorphism, because all isomorphisms do that. But now I have a choice, right? I could either do this, or I could do this. Right, and both of those are valid automorphisms. Okay, so we just discussed how the only isomorphisms from Z3 to itself are these two, right? So the one that sends everything just to itself, so I'll call that F, and the one that swaps 1 and 2, so I'll call that G. And that's all of them, right? We're forced into 0 goes to 0, and so then these are the only two options left, is do you leave 1 and 2 alone or do you swap them? So let's see what's the deal with combining these functions via composition. So what is F composed with F, right? Well, if you do nothing and then you do nothing again, surely that's the same as doing nothing, right? If you were to do F and then G, so first you do nothing and then you swap them, well, that's the same as swapping them. So F composed with G should be G. And similarly, if you first swap them and then do nothing, well, that's the same as just swapping them. And then now if you do G and then G again, right? So if you swap 1 and 2 and then you swap them again, well, then you're back to where you started. So G composed with G is the same as F. And so from this table, we can see it's a group. And this table should look kind of familiar, right? It looks just like the addition table for Z2. The only difference is we've changed the symbols, right? We've replaced 0 with F, we've replaced 1 with G, and we've replaced addition mod 2 with composition. But you can see it's the same table. It's just a change of names, right? So that's exactly what it means to be isomorphic. So this is phi, right? That's the set of all automorphisms of G. And this is Z2. And we see that they are the same. So there you go. So phi for that particular G is isomorphic to Z2. Now, I'm not sure I presented that super well. So here is a really good answer from a student. We see they started off with G is a group, and that's a set of all isomorphisms. So they started off by saying why it's got to be an isomorphism. Man, let me move my head out of the way. And then they said, well, it's got to have an inverse. It's got to have the identity. So that's why it's a group. And then at the bottom, you can see they're saying exactly what I was saying, which is that the isomorphism preserves identity. So 0 has to go to 0, which means the only other options are the one that does nothing and the one that swaps 1 and 2. And then he described it as U squared equals the identity, or mu squared equals the identity. I guess that's the names that he chose, which is totally fine. And if you're in a group where you're the only non-identity element, when you square it, it gets you to the identity, well, that's Z2, right? That's the way that Z2 works. So phi has got to be isomorphic to Z2. So there you go. So that's perhaps a better layout of an answer than what I did. This was 10 points. All right.